Alright, my internet I think went down. So are we back? Yeah, I think we're back on YouTube. And back on Twitch. Alright. Where was I? As an example, in the spatio-temporally ordered MBL DTC, the spectrum has a distinctive pattern of pairing between Schrodinger's cat states that are separated by an angle pi. Figure 1C. 1C is up here. Oh, these two things are both on the blue diagram. That makes more sense. So it's saying basically like this state and that state. Every eigenstate of the Hamiltonian, so every like equilibrium, every possible equilibria of the Hamiltonian that exists has a pair that's its inversion. Okay. As an example, in the spatial template, blah, blah. Yeah, right. This pairing manifests as a stable subharmonic response, wherein local observables show period double oscillations that spontaneously break the discrete time translation symmetry of the drive for infinitely long times. Show period doubled oscillations. Okay. So it says the fact that these things show up in pairs this pairing manifests as a stable subharmonic response, wherein local observables show period doubled oscillations that spontaneously break the discrete time translation symmetry of the drive for infinitely long times. I think this is saying that some of the particles in the system end up oscillating at twice the frequency of the Hamiltonian, so that the thing that's driving it changes. Seems weird, but okay. The unique combination of spatial long-range order and time translation symmetry breaking in an isolated dissipation-free quantum many-body system is the hallmark of many-body localized discrete time crystals. The unique combination of long-range spatial order and time translation symmetry breaking in an isolated dissipation-free many-body quantum system. Okay, so I guess they're just saying that like anytime you have, or maybe not anytime you have this, Okay. I mean, I guess they're just saying this happens in all of these systems where you have both long-range order. I guess the order in this sense is the fact that all of these average to a half. And I'm not really sure what long-range order, like in here it makes sense, you know, every particle has the same value, so they're all correlated. But here, every particle is in a superposition of 0, 1. Here we have 0, -1. Here we have 0, +1. Here we have 1, -0. Here we have 1, +0. So, I mean, I guess in every state is in a superposition. I guess this is what they're calling a Schrodinger's catch state. In particle physics, we call this a singlet state, or we call this a singlet state. All right, am I being stupid? Yeah. I guess when it's with two particles. But all right, they're calling it a Schrodinger's cat state. I know there's a better name for this. I just can't remember it off the top of my head. So move up here. Right, unique combination of long-range order and time translation symmetry breaking, and then isolated dissipation-free quantum many-body system is the hallmark of many-body localized discrete time crystals. Yeah, I don't get this. So I get the time translation symmetry breaking is essentially means this time crystal. So the thing, the state evolves periodically in time. I guess they're saying that plus the fact that the states have correlations in space. Okay. Is something that's always true in these many-body localized discrete time crystals. Experimentally observing a non-equilibrium phase, such as a many-body localized discrete time crystal, is a challenge due to limited programmability, coherence, and size of noisy intermediate scale quantum hardware. So this just means low number of qubits without perfect error correction. Subharmonic response by itself is not a unique attribute of the MBL DTC. Rather, it is a feature of many dynamical phenomenon whose study has a rich history. this is maybe worth looking up. Condensed matter people. Okay, this looks... They're just, that's why. Alright, what does it mean in the classical system? Oh no, this is quantum information. I guess subharmonic response just means the fact that there's something moving faster than the frequency of the oscillation. That doesn't seem right, but all right. See also chapter 8 and reference 12. More recently, we might want to see what reference 12 is actually. Can I click on that? Nope. A brief history of time crystals. Oh, that could be useful. More recently, or most recently, interesting discrete time crystal-like dynamical signatures have been observed in a range of quantum platforms. Such signatures, however, are transient, arising from slow or pre-thermal dynamics from special initial states, and are separated from MBL-DTC by a special phase transition where eigenstate order disappears. Thus, despite recent progress, observing an MBL-DTC remains an outstanding challenge. So I guess they're saying that their time crystal would last forever or something, whereas most of these time crystals that have been observed recently are decay eventually, or maybe aren't even really time crystals. Here we perform the following necessary benchmarks for experimentally establishing an eigenstate ordered non-equilibrium phase of matter. One, drive parameters are varied in order to demonstrate stability of the phase in an extended parameter region and across disorder realizations. When did they reference this figure? Figure 2? I don't see them reference it at all. Oh, down here. Okay. So we perform the following benchmarks. For establishing an eigenstate ordered non-equilibrium phase of matter. First, they vary the driving parameters to demonstrate the stability of the phase, and the extended parameter region across disorder realizations. Limitations of 2 finite size, finite coherence time are addressed respectively by varying the number of qubits in the system and by separating the effects of intrinsic decoherence from intrinsic thermalization. Limitations of finite size and finite coherence time. Okay, not really sure why varying the number of qubits helps with this stuff. Okay. The existence of eigenstate order across the entire spectrum is established. The flexibility of our quantum processor combined with scalable experimental protocols devised in the following allows us to fulfill these criteria and observe time crystalline eigenstate order. Okay. I've been at this for about an hour. I'm going to take maybe 5-10 minute break and come back here. I might switch over to this paper. It is obviously a lot longer, but seems like might be a little bit more accessible, this thing. Feel like I'm I don't know. I'll see how I feel in 5-10 minutes. Alright, I'll be right back. Do we have